So in today's video we are going to learn about the chemistry of carbohydrate. So what are the carbohydrates? As the name suggests, carbo means carbon and hydrate means water molecule. So carbohydrate basically contains carbon, hydrogen and oxygen. These are present in the molar ratio of 1 is to 2 is to 1. So basically carbohydrates are polyhydroxyaldehyde or ketone or the derivatives which are obtained from them. So they are polyhydroxyaldehyde or ketone. So polyhydroxy means they contain many hydroxy groups with functional group as a aldehyde, that is CHO, or ketone, that is C double. Now the empirical formula for the carbohydrate, empirical formula is CH2O by N, or you can write this as CnH2O N. Okay, so carbohydrate, as it contains carbon, hydrogen and oxygen, and we multiply that with n number of carbon atoms. So whereas n is equals to more than or equals to 3. So we'll take an example. So if you fill the n value as a 3, the formula becomes C3H6O3. So this is a molecular formula for glyceraldehyde. Glyceraldehyde. Okay, now this glyceraldehyde, it is also considered as a reference carbohydrate. Reference carbohydrate. Why it is that? Because this is the smallest sugar, or we can say this is the smallest monosaccharide or carbohydrate molecule from which all other carbohydrates can be formed by addition of carbon atoms. So we call it a reference carbon. So now we will see the functions of the carbohydrate. So what are the functions? So first of all, it is the source of energy in the plants as well as animals. So it is a source of energy. Second, it is also a storage form of energy in plants and animals. In plants, so storage form of energy in plants in the form of starch, and in animals like humans in the form of glycogen. Another use is this is a structural component of cell, or you can say cell membrane. This is a structural component, acts as a structural component it is also act as a exoskeleton in some animals and some plants, right? Molecule chitin acts as an exoskeleton in insects. Cellulose acts as a structural component or exoskeleton of plant cell. And glucopolysaccharides which are also called as glycosaminoglycans. These are also act as a structural component in animals, higher animals like in human. The next use of carbohydrate is the insoluble carbohydrates which are there, which cannot be digested by the human gastrointestinal tract. They act as a dietary fibers. So acts as dietary fibers like cellulose. Carbohydrate also acts as a component of nucleic acid. They act as a component of nucleic acid, like ribose, which is a sugar. It is a component or constituent of RNA, and deoxyribose, which is also sugar, is a component of DNA. So we'll see now the classification of carbohydrate. So the classification of carbohydrates is mainly based on number of sugar units. So in classification we have monosaccharides, we have disaccharides, we have oligosaccharides, and we have polysaccharides. So here the word saccharide in Greek means sugar. So as name suggests, mono means one and saccharide means sugar. So monosaccharides are the carbohydrates which contains only one sugar unit. As they contain only one sugar unit, we also call them as simple sugars. And as they contain only one sugar unit, they cannot be hydrolyzed further into smaller units. Cannot be hydrolyzed further. So this monosaccharide type of carbohydrates, they contain, as carbohydrates are the polyhydroxyl derivatives of aldehyde and ketone. So we can classify these monosaccharides again on the basis of presence of aldehyde group or ketone group. Okay. So if we classify on the basis of aldehyde, the monosaccharide which contains aldehyde, they are called as aldoses, and those who contains ketone, they called as ketoses. So we will see an example of this. So as you can see here, I have written molecular formula for the two compounds. Okay, so this contains aldehyde CHO group. Okay, this is a glyceraldehyde, and if you see here, this contains ketone group. So this glyceraldehyde is aldoses, and the molecule containing ketone group is dihydroxy acetone. Okay, this contains ketone group, so this will be classified as a ketosis. So these monosaccharides can also be classified on the basis of the presence of carbon atom. How many carbon atoms are present? So on the basis of number of carbon atom, it can be divided into triosis, tetrosis, pentosis, hexosis, and heptosis. So we can divide this classification like triosis, tetrosis, pentosis, hexosis into aldoses and ketosis. Okay. So here aldoses, and we will see which are the ketoses. So triosis with aldehyde group is glyceraldehyde, and triosis with ketone group is dihydroxy acetone. Okay. Triosis means it contains 3 carbon atom. Heptosis means it contains 4 carbon atom. Pentosis means 5 carbon atom. Hexosis means 6 carbon atom, and heptosis means 7 carbon atom. Okay, so tetrosis. For tetrosis, we have the aldolase, which is called as erythrose, and ketosis is erythrulose. Then for pentosis, we have ribose, and in ketosis, we have ribulose. For hexosis, in aldolase group, we have glucose. So we have glucose, we have galactose, and mannose. On the other hand, for ketosis, we have fructose, and for heptosis, we have pseudoheptose. Okay. So now, as we see this classification, we have done the classification on the basis of the presence of functional group which is present in monosaccharides, that is aldoses and ketoses. And now we have done the classification of monosaccharides on the basis of number of carbon atom present, that is thioses, tetroses, pentoses, hexoses and heptoses. So this glyceraldehyde molecule, what it is? It is an intermediate molecule. It is an intermediate. So as dihydroxyacetone, these are the intermediates of glycolysis process. Okay, erythrulose is also intermediate substance in pentose phosphate pathway. Okay, as of ribose, this is a component of RNA. Ribulose, it is also intermediate in pentose phosphate pathway. Glucose, galactose, mannose, those are the simplest sugar. Fructose is also called as a table sugar. And pseudoheptose is also an intermediate in pentose phosphate pathway. Okay, so this way we can classify the monosaccharides on the basis of number of carbon atom and on the basis of functional group present, that is aldehyde or ketone. On the basis of number of carbon atom present, we are classifying this as a triose, tetroses, pentoses, hexoses and heptoses. So for heptoses, as you can see, we don't have the aldose group. We don't have the molecule which comes under the aldose group. We only have a molecule which comes under ketosis group. So now we will see about disaccharides. So the second classification is disaccharides. So di means two, saccharides means sugar units. So these are the carbohydrates which contains two molecules, two monosaccharide units. It is two sugar units. So contains two sugar units, or you can say two monosaccharide units. So how the disaccharides are getting formed? So disaccharides are formed by two monosaccharides unit. Two monosaccharide units link together with the help of glycosidic bond, glycosidic linkage you can say, or glycosidic bond. So when the two monosaccharides in it get linked together with the help of glycosidic bonds, we get disaccharides. So there are two kinds of glycosidic bonds. That is O-glycosidic bond and N-glycosidic bond. So how you will get O-glycosidic bond and how you will get N-glycosidic bond? So when the carb molecule, which is a monosaccharide, joins with non-carb molecule, when carb molecule, if the carb molecule joins the non-carb molecule on its hydroxyl group end. So when the monosaccharide molecule joins on OH group end of the non-carb molecule, we get O-glycosidic bond, which is called as O-glycosidic bond or linkage. And if the carb molecule joins with non-carb molecule on its amino group. Okay, so the carb or monosaccharide unit, it joins on the amino group of non-carb molecule, then the bond form is called as N-glycosidic bond. N-glycosidic bond or linkage. Sugar to sugar linkage are O-glycosidic linkage. O-glycosidic linkage. So whenever we see a disaccharide molecule, we will always consider that this disaccharide is formed by the two monosaccharide units linked with O-glycosidic bond. O-glycosidic bond. So now what are the examples of disaccharides? Okay. So examples of disaccharides. The main examples are sucrose, we have maltose, and we have lactose. Okay. So this sucrose molecule is made up of one glucose molecule and one fructose molecule. This maltose is made up of glucose molecule with glucose molecule. So two glucose molecules combined together forms a maltose. One glucose molecule combines with one fructose molecules form a sucrose, and one glucose molecule combined with galactose, we get a lactose. So we'll see one by one each of these disaccharides. So we'll see a disaccharide called as sucrose as an example. So as sucrose is a combination of glucose plus molecule of fructose. So as I told you earlier, all sugar molecules are linked with O-glycosidic bond. So we'll see now the how formation of sucrose and the glycosidic bond takes place. Okay. So this is a glucose molecule, which is a ring. I have represented here in the ring structure. So this glucose molecule and one fructose molecule. Okay, these are the pyranose ring and this is the furanose ring. This fructose and glucose molecule will go into dehydration or condensation process. So this one glucose molecule and one fructose molecule, they will combine each other, and with the dehydration or condensation process, will lose one water molecule like this, and there will be formation of glycosidic bond. Now the glycosidic bond forms here in between. This is the first carbon atom of glucose, and this is one carbon atom of fructose. This is 2, third, fourth, and fifth. So when we remove the one water molecule from combination by combining one glucose and fructose molecule, what happens is this fructose molecule will rotate itself so that the second carbon atom which is present on the left side will turn itself and come near to the glucose molecule, so that if we see here in the formation of sucrose, this is the first carbon of glucose, first carbon atom of glucose, and here this is the second carbon atom of fructose. Okay, so this second carbon atom which was on the other side, so the molecule turned itself, and this molecule will, the second carbon molecule will come closer to the glucose molecule. So now the formation of O-glycosidic bond is between one glucose molecule and between two fructose molecules. Means first carbon of glucose molecule and second carbon of fructose molecule. Okay, so this is an alpha glucose. This is alpha glucose. The configuration of glucose is alpha. Why it is alpha glucose? Because this OH group, which is on the first carbon atom of glucose, is far away from the CH2OH group, which is 6 carbon atom. So this is far away. That's why it is alpha configuration of glucose. Okay. Now here in the fructose, this OH group is near to the CH2OH group of the last carbon atom in fructose. This is near. So that's why this configuration is called as beta fructose. Okay. So alpha glucose combines with the beta fructose and gives us the sucrose, which has a glycosidic bond, O-glycosidic bond, which we can term as 1 alpha 2 beta O-glycosidic bond. This sucrose is a non-reducing sugar. Non-reducing sugar. Okay. All the monosaccharides are reducing sugars. What does it mean by reducing sugar? When the monosaccharide unit combines with the Benedict's reagent, okay, they give a reaction. So that those who give the reaction with Benedict's reagent, we call them reducing sugars. It is also called as table sugar. Okay, so this is a sucrose molecule, which is a disaccharide, which contains glucose, one molecule of glucose and one molecule of fructose. So when the alpha glucose molecule combines with the beta fructose molecule, with the process of condensation or dehydration, with the removal of water, we get a sucrose molecule which has 1 alpha 2 beta O-glycosidic bond. Second example is lactose, which is formed by the one molecule of glucose plus one molecule of galactose. Okay, and this lactose, it is present in milk. And it is also reducing sugar. Okay, this lactose contains beta 1,4 O-glycosidic bond. So the first carbon atom of galactose get linked with the fourth carbon atom of glucose and gives us, and this both galactose and glucose are in beta configuration. So we say the bond is beta 1,4 glycosidic bond. So lactose, it is a disaccharide which is made up of glucose molecule and galactose molecule. It is present in milk. It is a type of reducing sugar and it contains beta 1,4 glycosidic bond. Then third disaccharide is maltose, which is a combination of two glucose molecules having alpha 1,4 glycosidic bond. So the first carbon atom of one glucose molecule linked together with the fourth carbon atom of second glucose molecule forming alpha 1,4 glycosidic bond. So these are the examples of disaccharides. Now we'll come to the oligosaccharides. So the third type is oligosaccharides. So oligo means few, saccharides means sugar. So these are the carbohydrates which contains few sugar units. How few? That is 3 to 10. 3 to 10 monosaccharide units. Monosaccharide units. So oligosaccharides can be classified like disaccharides, tetrasaccharides, and so on. Once monosaccharide units reaches or goes beyond 10 monosaccharide units, so more than 10 monosaccharide units gives us polysaccharides. These are referred to as polysaccharides. So number 4, polysaccharides. Okay. So poly means many, saccharide means sugar. So polysaccharides are the carbohydrate groups which contain more than 10 monosaccharides in. Okay. And this polysaccharide carbohydrates can be further divided into homopolysaccharides or heteropolysaccharides. Homopolysaccharides or heteropolysaccharides. So what is the difference between homopolysaccharides and heteropolysaccharides? What are the homopolysaccharides? Homopolysaccharides are the polysaccharides which contain same or only one unit of monosaccharide. Okay, or only one unit of monosaccharide. And heteropolysaccharides, they contains more than two or different monosaccharide units. Okay, they contain different monosaccharide units. So homopolysaccharides, what are the examples of homopolysaccharides? So the examples are glycogen, okay, cellulose, then we have inulin, we have starch, so homopolysaccharides are polysaccharides which contains one single unit of monosaccharide. Examples are glycogen, cellulose, starch, inulin. Heteropolysaccharides on the other hand, they contain different monosaccharides unit. And the examples are agar or agarose, pectin, and mucopolysaccharides. Mucopolysaccharides, which are also called as glycosaminoglycans. In this video, we are not going to cover the heteropolysaccharide part. We are going to only talk about the homopolysaccharide part. And in the next video, I will continue with the heteropolysaccharides. Now we will talk about homopolysaccharides, which are also called as homoglycans. This polysaccharide is called as glycans. Okay, so I have told you the examples of homopolysaccharides. Homopolysaccharides are these are the polysaccharides which contain a single unit of monosaccharide in its side in its chain. Okay, the examples are starch, glycogen, cellulose, and inulin. So we'll see those examples one by one. We will start with the starch. Starch. So what is starch? It's a storage form of energy. Okay, it's a storage form of glucose. You can say storage form of glucose in plants. Okay. Now this starch is made up of This is made up of lot of glucose molecules. It is mainly glucose molecules joined together by a linkage in a long chain. And this starch molecule can be unbranched or it can be branched. Also, the source of starch is rice, wheat, potatoes, etc. Okay. So now we will see how the structure of starch. The starch. Okay, so now here we have this. These are glucose molecules linked together. Now we will zoom out this part. We will zoom out this part. And we will see how the bond formation occurs in starch molecule. Okay, so we have zoomed into this portion of starch molecule. We will look for the to understand the bond formation in the starch molecule. Okay. So these are the glucose molecules. These are all glucose molecules, okay, which are in the configuration alpha configuration. So the glucose molecules, two glucose molecules are attached to each other with the help of glycosidic bond, which is formed between this glucose molecule's first carbon atom and this glucose molecule's fourth carbon atom. 1, 2, 3, 4. Okay. So this bond is, we call this bond as alpha 1,4 glycosidic bond. Okay. As these are the alpha units of glucose, alpha configuration, and the first carbon atom of one glucose molecule gets linked with the fourth carbon atom of second glucose molecule, forming a bond which we call as alpha 1,4 glycosidic bond. But there is one more bond which is present. This is the sixth carbon compound of one glucose molecule. And this is first carbon compound, carbon of glucose and six carbon of glucose, which is called as, we call this linkage is called as alpha 1,6 glycosidic bond. Okay. So there are two bonds present in sucrose molecule. So the continuous chain of glucose molecules linked with each other with the help of alpha 1,4 glycosidic bond, and the branch chain of glucose molecules are linked with alpha 1,6 glycosidic bond. Okay. So as I told you earlier, the starch molecule can be branched or unbranched. It is unbranched. Okay. If starch molecule is unbranched, then it contains alpha 1,4 glycosidic bond. Okay, as you can see here, the alpha 1,4 glycosidic bonds are formed between two glucose molecules. Those are subsequently linked to each other. Those are in a straight chain. So there is no branching. So if it is unbranched small starch molecule, the glycosidic bond linkage bond will be alpha 1,4 glycosidic bond. Unbranched unit of starch, or you can say unbranched subunit of a starch, called as amylase. Okay, this is called as amylase. We can say polymer. This is the amylase polymer of starch. Okay, and if this starch molecule is branched, if it is branched, it contains alpha 1,4 bond. It contains alpha 1,4 glycosidic bond, as well as you can see here, it also contains alpha 1,6 glycosidic bond. Okay, and this kind of polymer which is branched, it is called as amylopectin. Amylopectin polymer of starch, which is a branch. Now, what is the significance of these two molecules? Okay. So, what happens? when this starch will digest in the intestine, when it goes to the intestine, the salivary amylase, when it comes to the mouth, first of all, the salivary amylase, and when it goes to the intestine, there are pancreatic amylase. So this both amylase, which are salivary amylase and pancreatic amylase, those are alpha amylase, and this amylase is, okay, the salivary amylases and pancreatic amylases. Okay, this both amylases, they act randomly. They act on random alpha 1,4 glycosidic bond. So, when we want to digest the starch molecule, okay, problem is the salivary amylase and pancreatic amylase, which are both used for the digestion of starch. They are alpha amylase, and they acts mainly on random alpha 1,4 glycosidic bond. So what happens when the digestion process occurs in the intestine? Okay, this starch molecule gets broke down into smaller units, or some units will be smaller and some units will be large. Okay, so you consider if this alpha 1,4 glycosidic bond is broken by the pancreatic amylase or salivary amylase, we will have a smaller unit of this and we will have a larger unit of this, because they are breaking the alpha 1,4 glycosidic bond randomly at random positions, which is alpha 1,6 glycosidic bond. So this pancreatic and salivary amylase, they cannot break down this alpha 1,6 glycosidic bond. As a result of this pancreatic and salivary amylase cannot break down the alpha 1,6 glycosidic bond, and they are breaking alpha 1,4 glycosidic bond at random sites. We get a long and short chains of branched and unbranched molecules of starch, which are called as dextrins. So we get molecules called as dextrins. Okay. So what are these molecules? Dextrins are hydrolyzed product of starch. Now we will talk about glycogen. It is a storage form of glucose in animals like humans. It is also mainly consists of alpha glucose. Okay. So these glycogens can be branched and it can be unbranched, like we saw in case of starch. Okay. This glycogen has another name which is called as animal starch. Animal starch, as it is kind of similar to the starch which is in plant, but this is in animals. And in our body, whenever there is excess of glucose, that glucose is stored in the form of glycogen. What are the main organs? Liver and muscles. Here we have alpha 1,6 glycosidic bond, and here we have alpha 1,4 glycosidic bond. Okay. So as we have seen previously in starch, it also contains alpha 1,4 glycosidic bond and alpha 1,6 glycosidic bond. The difference between starch and glycogen, that's the branching, you can say, branching in glycogen is more extensive than starch. So how so? How the branching in the glycogen is more extensive than the starch? So here branches occurs in glycogen after 8 to 12 glucose residue molecule. So 8 to 12 glucose residue molecule as compared to in starch after every 20 to 30 residues, that is glucose molecules, we find a branching. So branching is quite compact here in the glycogen molecule than as compared to starch. Okay, so now we'll talk about cellulose. Cellulose, it is also a homoglycan. Okay, it is mainly obtained from the foodstuff like grands, flours, and tubers. Okay, this also contains glucose molecules, and cellulose is mainly unbranched. Okay, there are no branches. So we see the molecule how it looks like. So this is the spread glucose chains which are present in cellulose. Okay, these are the straight chains. So no branching there, and this is the structural component in plant cell. You can say plant cell wall. Okay, and the main bond which is present here is glucose molecules. These are the glucose molecules. These are the glucose molecules. Okay, these glucose molecules are linked together with the help of beta 1,4 glycosidic bond. Okay, so the main bond present in between two consecutive glucose molecules are beta 1,4 glycosidic bond. There is a formulation of compact structure here. So this adjacent glucose molecules are linked with the beta 1,4 glycosidic bond, and they are stashed over each other with the help of some hydrogen bonds in between them. So we don't have any enzyme which breaks beta 1,4 glycosidic bond. That's why we cannot digest cellulose. And as we cannot digest the cellulose, this cellulose works as or acts as a dietary fiber. Okay. So this cellulose acts as a dietary fiber. Why? Because our GI system doesn't have or doesn't consist any enzyme which can break beta 1,4 glycosidic bond. That's why it cannot be digested in the GI tract, and that's why it is considered as a dietary fiber. Firstly, we will talk about dextrans. Okay, so let me first make it clear for you guys. Okay, the dextrins which we studied, this is different terminology. Dextrose is different. Okay, okay. These homopolysaccharides, these are highly branched. These dextrans are highly branched, and they contains alpha 1,3, alpha 1,4, and alpha 1,6 glycosidic bond. The extrans acts as a structural components in some bacteria and fungi. Since these extrans are highly branched, they don't go out of vascular compartments. Vascular compartment, and because of this reason, they are used as they are used as they are used as plasma volume expander. So they are used as a plasma volume expander, as in case of hypovolemic shock. Okay. So the extras, these are homoglycans or homopolysaccharides which are highly branched. They contains alpha 1,3 glycosidic bond, alpha 1,4 and alpha 1,6 glycosidic bonds. These are the structural components in some fungi and some bacteria. And because of highly branched structure, they don't go out of the vascular compartment, so they remain in the vascular compartment. So because of that, they are used as a plasma volume expander, which we can be used as a treatment modality in hypovolemic shock. As I have mentioned earlier, the dextrins and dextrose. So what are the dextrins? Dextrins are the hydrolyzed product of starch. Okay, these are the dextrins. And dextrose is simply alpha glucose. You can say D glucose, alpha D glucose. Okay, this dextrose we use as a infusion. We use for the purpose of infusion in normal medicinal practice. Okay, so I hope you guys understood the carbohydrate chemistry and classification of carbohydrate. So we have learned the classification monosaccharides, disaccharides, and then polysaccharides. In polysaccharides, we have learned about the homopolysaccharides, and we have seen the examples, various kind of examples of homopolysaccharides with their uses and their molecular structure and bond formation. So in our next video, we are going to cover heteropolysaccharides. See you there.